Hey friends, welcome back to Candy Code. In this video, we are going to look at the first and last occurrence problem using divide and conquer method. But before we proceed, if you haven't subscribed yet and you like what you see, do consider hitting the subscribe button. This encourages YouTube's algorithm in promoting more of our videos to more people out there. Let's get started with the problem statement. Given sorted array with possibly duplicate elements, the task is to find indices of first and last occurrences of an integer or element x in the given array. For instance, if the input array contains 1, 3, 5, 5, 5, 67, 123 and 125, and the element to be searched is 5, then it must return the index values 2 and 5 as the first occurrence of 5 is at index position 2 and the last occurrence of 5 is at index position 5. The naive approach is to iterate throughout the array when we find the element for the first time. We update the index position of first and last. We keep updating the last index for each time when we find the element x. In this case, it is 5. We begin from the index position 0 and check if the element present at the 0th index is the element that we are searching for. Since array of 0 is not equal to 5, we proceed to the next element. Since array of 1 is also not equal to 5, we move to the next element. Here, array of 2 is equal to 5, and so we initialize first and last at the position 2. On the further iterations, we discover that array of 3 is also equal to 5, but this time we are only going to change the value of last. In the next iteration 2, we discover that array of 4 is equal to 5, and so we update the value of last variable. And in the next iteration 2, since array of 5 is 5, we update the last variable. At last, when we move to array of 6, since array of 6 is not equal to 5, we do not update the last index and we keep checking throughout the length of the input array. At last, the first and the last variables will be pointing to the first occurrence and the last occurrence of the element searched. Let's look at the algorithm. Let first and last be the variables of the data type integer and initialized to -1. We run a for loop from index 0 to n-1. If the element being compared is not equal to the element being searched, we return the next iteration. In case if it matches for the first time, we update the value of the variable first and we update the value of variable last. Every time when we find x in the array, we keep updating the value of the variable last. At the end of the iterations, first and the last variables contain the values of first occurrence index and the last occurring index respectively. If the element being searched is not found in the input array, then we return -1. The time complexity of this algorithm is order of n, where n is the length of the input array. The worst case happens when the element x being searched is not found in the input array. The space complexity of this algorithm is order of 1. The frequency count for other operations in this algorithm is of same order as that for element comparisons. When the elements in the input array are polynomials, vectors, very large numbers or strings of characters, the cost of an element compared is much higher than the cost of other operations. Hence, the time is mainly determined by the total cost of the element comparisons. Naive approach requires n comparisons in the best, average as well as the worst cases. The divide and conquer algorithm for this problem is very similar to the binary search algorithm. If you haven't watched it yet, do check out the video link provided in the description or the link which pops up in the suggestion. Alright, let's get back to the problem. Now let's look at the detailed solution approach. This time, let's say the input array contains 1, 3, 5, 5, 5, 5, 7, 123 and 125. Let the value of x, that is the element being searched, be 5. At first, we compute the mid for the entire array. Although the array of mid is 5, we cannot directly return this index. In order to find the actual first occurrence, we need to check the element previous to the mid. Only if the previous element is not equal to the element being searched, we proceed to return the value of mid. Otherwise, we'll limit our search to the first half of the input array and repeat the same until the value of low becomes greater than high. To find the index of the last occurrence, we follow a similar approach, but this time we have to compare the value next to the index of mid. Only if the array of mid plus 1 is not equal to x, we proceed to return the value of mid if the array of mid is equal to x. Otherwise, we shift the search to the latter half of the array and repeat the same until low value becomes greater than high value. First, let's look at the recursive algorithm. Let's assume array to be the global array. Then we divide the problem into subproblems to find the first index. If the element x is not found in the input array, we will return -1. We repeat almost the same procedure to find the last index. Time and space complexity of this algorithm is order of log n, where n is again the length of the input array. In case if you are concerned about the storage space, you can opt for the iterative approach. This approach remains same, but instead of using recursive calls, we perform iterations and modify the value of low and high variable. We repeat the same with slight modifications to obtain the last occurring index. Time complexity is order of log n, whereas the space complexity is reduced to order of 1. In case of unsuccessful searches, the time complexity is order of n for best, worst, as well as the average case. The best case for a successful search occurs when the middle element of the array is the only element being searched. So the best case time complexity is order of 1, whereas the average and the worst case time complexity for successful search is order of log n. At first, we need to assume that the iteration in the binary search terminates after k iterations. At each iteration, the length of the array is halved. So let's say that the length of at any iteration is n. So at the very first iteration, the length of a, that is our array, would be n, and at the second iteration, as we have told earlier, it would be halved. Therefore, length of a is equal to n by 2. Again, in our third iteration, as you can see, n by 2 will be further reduced to n by 2 by 2, which can be simplified to n divided by 2 to the power of 2. Likewise, after k iteration, we'll have length of a as n divided by 2 to the power of k. After k divisions, the length of the array becomes 1. Therefore, we equate the above equation to 1. Now the equation reads as length of a is equal to n by 2 to the power of k, which is equal to 1. Again, we further simplify it as n is equal to 2 to the power of k. Applying log on the both sides of our previous equation, we tend to get log of n is equal to log of 2 to the power of k. Since log of a to the power b can be simplified as b log of a, we have reduced that to k log of 2. Further, log to the base a of a is 1. Therefore, here we can reduce log of base 2 of 2 to 1. Therefore, the time complexity is log of n. Please like and share this video if it helped you. It could help someone else too. The complete solution code is provided in the description below. Don't forget to hit the subscribe button for more videos. Thanks for watching. We'll see you next time.